Howdy, so for science I'm looking at atomic spectroscopy. So science understandings that you're going to cover are that flame tests and AAS are used to identify elements, and it relies on electron transfer between atomic energy levels, so you need to explain how that happens. So with absorption and emission, you need to explain that the wavelengths of radiation emitted or absorbed by an element are unique to that element, and that can be used to identify the substance in a sample. And you need to explain why radiation emitted or absorbed is unique to that element. And then you need to explain the principles of AAS in identifying elements in the sample. So we know that electrons exist in shells around the nucleus. So if we look at hydrogen here, we can see we've got one electron in the first shell, and then there's other shells that the electrons can move to if they're hit with energy. So when we add energy, the electron jumps up into what we call an excited state, and then eventually it jumps back down. When it jumps back down, it releases a photon of energy. So the electrons can be pushed up into energy shells that are further out, and that requires energy, and then when they fall back down, they release energy in the form of light. So when the electron jumps up, it absorbs energy equal to the energy required to jump it up, and when an electron jumps down, it releases energy in the form of a photon with a wavelength equal to that of the energy difference between the electron shells. There's a lot more of this in physics than there is in chemistry, but this is just the basis of how AAS works. So here we have a picture of the energy levels in hydrogen. So here's the ground state, this is where the electron normally is, and then we have the first excited state, second excited state, and so on. So there's a difference in energy between these energy levels, and if we supply a piece of energy with that amount of energy, it will jump up from the ground state up to the first excited state. So we see the electron absorbs the energy and it jumps up to the first excited state. Like I said, that gap there represents a difference in energy, and that energy is needs to be provided by that light. If you provide a little bit too much or not enough, it won't go up. The electron will then jump back down from the excited state to the ground state, and when it does that, it releases a photon of energy. Again, equivalent in energy terms to the difference in energy between those two states. So different photons with different energy give off different wavelengths of light. So this is called an atomic emission spectrum. And again, this is hydrogen, so we can see we've got jumps from one higher energy level down to a lower energy level, and when that happens, the photons are released and they have a specific wavelength. In this case, the jump from 6 to 2 is quite a big gap, so it's high energy, so that's purple. Whereas if we look at the jump from 3 to 2, that's a much smaller gap, that means that's lower energy, so we have a red photon being emitted. Now this works in two ways. You can either get the atom absorbing energy and then re-radiating it off, and that gives you the emission spectrum, or you can shine a spectrum of light on the gas that you're looking at, and it will absorb the energy that's equal to the energy gaps, so you have what we call an absorption spectrum. So this is showing where the light energy is absorbed for the excitement to happen. So they're basically the opposite of each other. So each atom or ion has different numbers of electrons in different shells. So what that means is you have different energy gaps all over the place, and that means that the electrons move into different energy states when they're excited. So because each atom or ion is different, that means that you're going to get different spectra being produced, so different emissions of light. So here's an absorption spectrum from the sun. We can see particular energy gaps, and they match up with several different elements that we'll see. So here we have hydrogen again, so we can see that this band here, this emission spectrum, matches up with that absorption spectrum part of sunlight. So that tells us that there's hydrogen in the sun. Down here we have helium, and if we look at this bar here, we can see that this one lines up perfectly with the absorption spectrum of the sun. So that tells us that there's helium in the sun, and so on and so on and so on. Down here we have uranium. We can see uranium's got a lot of electrons, so a lot of energy shells for the electrons to go into as well, so we can see that the electrons jump up and down and we get a lot more spectra than we do for hydrogen or helium, for example. So since different elements give off different spectra, we can find a way of looking at the spectrum produced by a sample to figure out if you have that element in the sample. So that's a qualitative. So is there any of this in this sample? And that's the principle behind this machine here called an atomic absorption spectroscope. And we'll go through how that works. So in an AAS, you shine a particular light through a sample that you've vaporized. That sample will absorb some of the light that is produced by the lamp, and the amount of light that's absorbed by the sample is proportional to how much of a particular element you have in the sample. So let's see how that works. So you have a lamp. That lamp has to have a particular element in it, and that element is what you're looking for. So if you're looking for lead, you need to have a lead lamp. If you're looking for silver, you need to have a silver lamp. You then have a sample that you vaporize, so that passes into an acetylene flame, so that vaporizes the sample, and that causes the ions to be floating around in here. So the light produced from the lamp passes through the sample. On the other side of the sample, you have a UV vis detector that detects how much light is being absorbed essentially. So you have an amount of light being produced by the lamp. Some of that light is absorbed by atoms in the sample, and that reduction in absorption is picked up by the UV vis detector and determined by the computer, and you get a pretty number coming out. That number is an absorbance number. So you can ask your computer to make a graph, or you can just ask it to give you a number, and that number is the absorbance. So if we have a look at this one here, we can see we have an absorbance number here, and that's the number that you could record. It's important to note that, like I said, the lamp that you use has to be specific to the sample that you're analyzing. So if you want to look for copper, you need to have a copper lamp producing the wavelengths that are particular to copper, so that any copper in the sample will absorb those wavelengths that are being emitted by the lamp. So let's look at a question. It says cobalt is obtained from sulfide ores. AAS is used to determine the percentage of cobalt in the ore. We get this calibration graph. So like I said, I had another video where I went through how to make calibration graphs, so you can have a look at that if you'd like. It says 10 grams of ore was crushed, made up to 100 ml solution, absorbance of 0.08 was recorded, determine the concentration of cobalt. So what we're going to do is we're going to find the concentration by using the calibration graph. So it says the absorbance is 0.08. So I'm going to draw a line from 0.08 across until I cut the curve, and there we go. And then from there we need to figure out what the absorbance is, so I'm going to draw a line. We need to figure out what the concentration is, so I'm going to draw a line from the top down. So now we can see that it cuts the line at around about 6.7, we'll probably say, so it's 6.7 milligrams per mil, so I'll write that in. 6.7, the unit is milligrams per mil. So the next part of the question says, calculate the mass of cobalt in 100 mils of solution. So we had 6.7 milligrams per milliliter. We've got 100 milliliters, so we're going to times that by 100. 6.7 times 100 is 670 milligrams, so that's in mass. So we times by 100 mils, so that cancels out those two. There we go. So we get 670 milligrams. Next part of the question says, calculate percentage by mass of cobalt in the sample. So we've got percent weight for weight. It's going to be equal. So we had 670 milligrams, which is 0.67 grams. We'll leave that as 0.67. How do I know that? There's 1,000 milligrams in a gram. We've only got 670, so it's 0.67. That's out of a total of 10 grams. Then to find percentage, we times that by 100. So get rid of that, so 0.67 times 10, so that's 6.7%. So get 6.7% weight for weight cobalt in the 10 gram sample. So today on Flipping Science, we looked at how AAS works. That's it for Flipping Science today. See ya.